All right, ladies and gentlemen, I'd like to invite you and welcome you once again to the AI and Data Science sessions. You are at track number 1 at the main hall and invited to speak to us today all the way from Australia is Professor Damminda Alahakoon. Now, Professor Alahakoon is a professor at the Trobe University in Australia, and he is a founding director of the Research Center for Data Analytics and Cognition at the Trobe University. He serves also as a visiting professor at the Lulea University of Technology in Sweden and the University of Moratuwa here in Sri Lanka. Professor Damminda has over 15 years of experience as an academic and in several Australian universities, as well as over 10 years in the IT and finance industries in Sri Lanka, in Australia, and also in the Netherlands. He obtained his bachelor's from the University of Colombo, Sri Lanka, and his PhD from Monash University in Australia. His research is focused in the area of machine learning, artificial intelligence, advanced data analytics, text and social media analytics, business intelligence, and the harnessing of such theories for practical tools and innovative technology for the industry. Ladies and gentlemen, I won't take any more of his time. Professor Damminda, thank you so much for being with us, and over to you.
Thank you very much. That's a very kind introduction. Can you all hear me? Or am I?
Yes, Professor, we can see you, and
right.
you are audible as well.
Okay, thank you so much. I'll share my screen. I have some PowerPoint slides, and let me. Okay, am I on?
Professor, we don't see the shared screen. Yes, it's on this. It's up now.
All right. Okay. All good?
Yeah.
All right. Okay. So I'm not sure. I'm supposed to go in for about 30 to 35 minutes, and if I'm going over, or if you want me to sort of stop, please let me know. But I'll try to keep to the timeline. Sometimes when I'm talking about something, an area or something that I really like, I just tend to sort of forget the time. So please don't hesitate to stop me if I'm going overboard. So thank you so much again for the very kind introduction. Artificial intelligence is an area which I've been involved in, I've been working in for more than 2 decades. Fascinating area, but it's become a term that is spoken and known by almost everybody. Mostly good, but I think some people are, or some parts of the community are starting to get quite worried about AI as well. So my talk today, I thought I'll go into a little bit of history. How did AI, the term and the work in AI began, and how it evolved, what has to be the future, considering the developments in technology, in computing, and the way that we live, and so on, and the so-called information age, and some ideas, some thoughts on how AI has to develop into what we have called this artificial general intelligence. And whether we like it or not, we are expecting things from AI, or I can't say it's a help. It's AI to be part and parcel of our society. And what this should be, what should AI in this new world look like? And should AI start thinking for themselves and doing things to help us by themselves? So the term AI, or artificial intelligence, was coined in 1956. It was a few decades ago, but not that far away. At a very famous conference, or we can call it the Dartmouth Summer Research Project on Artificial Intelligence, 1956. The picture on the right-hand side is a plaque that was put up more recently in 2006 to in that the place, and these men, 10 men, well, there are not 10 here, but it was a group of 10 men who were invited to spend almost 2 months together. Most of them spent 2 months, not all, thinking about intelligence in artificial form. And we call these people the founding fathers of artificial intelligence. And that was in 1956, but this is what they look like in recent times. They are not with us anymore. But you will recognize, I'm sure, people who are, many of you will recognize quite a few of these names. John McCarthy is credited with actually coming up with the name or the term artificial intelligence. Marvin Minsky from MIT, who passed away a few years ago, is called the father of artificial intelligence. Claude Shannon invented information theory. Ray Solomonoff, again, an intellectual who invented something called algorithmic probability. Alan Newell, computer scientist and cognitive psychologist. Herbert Simon, a political scientist, and a lot of contribution to AI, and so on and so forth. Now, we can see here that 10 of the brightest and the minds and the intellectuals were invited. And I'd like to sort of show you this part of this document, which proposed this workshop. Get these 10 men, and of course, it's a 10-man study. There was no gender balance and so on those days. It was the men who did those things, but that, of course, have obviously now changed. So they got together and discussed, worked together for 2 months. But what I'd really like to highlight, what I have underlined here, is that at that time, at the beginning, the thought was to build an artificial machine or machine intelligence that acted like, or that could almost mimic human behavior and thought processes. So that's what I have highlighted there. The reason that I'm highlighting it here is that this idea, this direction of AI, this expectation from AI actually changed after some time. Again, when we look at the evolution of what we call artificial intelligence, pre-1950, before the term AI was coined or the term came into use, something like AI or artificial humans, the thought or the idea was around even thousands of years ago. You would have seen different mythology, Greek, Indian, Chinese, and so on, where there were more humanoid robots. So it was machines that looked like humans and behaved and acted like humans. Then, of course, the birth of computing, and the computing provided the base, the foundation on which a softer machine. Machines did not have to be, this steel or metal things that moved and did. It was the soft machines came about with the computing, era of computing, and things changed. Then, of course, the connectivity, cloud computing, mobile, internet, and of course, the societies change with the way that we socialize, work, and live change. Of course, with the advent of the internet and so on. So this AI, what it was and what it has become, was found based upon these changes in society, technology, and computing. What we have today is a very different expectation from AI, and there are reasons for that. And I will go into a little bit of that later. But what we are expecting is humans, or what we are finding out is that artificial intelligence that coexist with humans, because there is a need for that. Again, evolution of AI, there has been ups and downs. So from the 50s to about the late 60s, there what we call the golden summer of AI. Then there was a book written by Marvin Minsky and a fellow called Papert, where they proved that the so-called AI or neural networks at that time could only solve linearly separable problems. And because of that, many of the researchers and research funding, especially in the US, was withdrawn from the AI. And then there was the decline, but then again, further some researchers persisted, and there was what we call the second summer, and much later, what we call the more recent, the current boom in AI with the deep learning to, it's not just the invention of deep learning and many other such techniques, but it's the computing power, technology, the connection, internet, but most importantly, how we live. So again, from from humanoid robots to computing, and housing the AI, which made the advances much faster, and developments in mathematical and information theory and computing technology by Wiener, Claude Shannon, Alan Turing, and so on, really provided the inner components with which AI could advance. And then, of course, this term called machine learning. Many people ask, so what is AI? Machine learning is the same thing. Well, it's used in the same meaning in most cases, but machine learning is slightly different. It's the reason that I showed you that the document on the founding fathers of AI and their expectation and what machine learning is doing is different. Machine learning is not about mimicking the brain. It's about making use of massive volumes of data in digital form so that we can generate patterns and insights from that. It's not about actually being a brain. So the things change over time. So why did this change? Is that so it's the main reason is what we call this information age or the digital age. That has resulted in a change in a shift in what we call the role of AI. So what is big data? It's lots of data. It's not just the volume of data. It's the diversity of the data from images, videos to audio, many forms, and especially with the IoTs, the wearable sensors, and many other forms. So what we have is almost a complete or somewhere close to a virtual or a digital version of our natural world is being created. So we are born with, say, or nature or God-given ability to sense the natural world, but this digital world that we have created, which is around us and which we need to work and interact with, we don't have a naturally given way of sensing and interacting with this. So one way of thinking of technology now, and especially that's why the AI is being advancing so much in so many ways, is that we now require another sensing capability over what we call our five senses also, and that's what AI is. So so the traditional practice was in the past, and in many cases even now, is that you get a data set which is representing a particular selected part of our environment. So for example, it could be a video data set, or it could be some IoT data. And then you build an AI to analyze or run or model that data. And then you get output. So the human selects the data, builds the AI, runs it just like a tool, and then gets some output, which we then interpret. So the intelligence comes from the human. But with this big data or digital information age and the environment, we do not have to do that. It's not possible for us to do that. That's not what we want, because digital data is being created all the time. So we want technology, machines, and AI to be able to continuously interact with it. Not for us to, it's not possible, and we don't want to actually sit and select particular parts of that digital. We don't know which ones to select. So because as I said before, the role of AI is almost to be the other sensing capability over the so-called five senses that we have. So it's AI that coexists with humans. All right. From there, if we really look at it, although we have lots of AI computational achievements, there's still uh, many aspects. Although, like for example, speed, processing speed, and many other capabilities are there. There are many aspects which the AI is really lacking and is not capable of achieving. And people say creativity, common sense, general purpose. But some of you, especially with the recent advances in the chat GPT is and so on, would think that, oh, it's already achieved creativity. Well, this is a debate that we can go into, but unfortunately I don't have the time. And I think there was a large language model talk earlier as well. So I wouldn't go into, and I don't have the time to go into LLM, but one comment that I can make is that no, although large language models do show, or in some cases, capability almost like creativity, it is not really creativity. It's something else, but that's a debate for another day. Okay, getting back to AI. So Marvin Minsky was called the father of artificial intelligence. He called that so this is a very general statement some time ago. AI is the science of making machines do things that would require intelligence if done by men. So that's a broad, a bit of abstract definition that and then, of course, the purpose here is that I'd like to introduce a couple of terms. It's important to know this. So the type of AI that's traditionally used, what I call, say, use humans select the data set, builds the AI, and runs it with a particular specific task in mind, it's called weak AI, or it has also been called artificial narrow intelligence. It's on a specific, narrow, and very clearly defined task. On the other hand, if we move to the human-like intelligence, the AI that can mimic almost identical human intelligence, then we call it strong intelligence. And this has to be general in the sense if we do not have to, or in many situations, if we cannot define what data to look at, what information to look at, what data sources to bring together, and we even do not want to or cannot say what is expected from the AI, then that is general. So that is where this term artificial general intelligence has come about. Again, I know that it looks like I'm jumping from to a completely different sort of topic, but no, it's important to understand or position what we have now and where we are going. We need to know these two terms for those who are not familiar with this: symbolic and sub-symbolic. What we had, or the AI, the initial AI that we are used or initially built, was called symbolic artificial intelligence, or what we call the classical AI. And it has also been called the good old-fashioned artificial intelligence. And those who are familiar with the area or even computing will know of or can think of these as rule-based systems, expert systems, and so on. There's a lot of advantages there, but you know that it has there. This has to be data engineering has to go in. What is engineering is that people or humans with knowledge has to build those rules or build the knowledge in. But there's advantages. For example, on the left-hand side, if you look at, this is an apple. The apple, so there's the origins of the tree, there's the body, stem, fruit. So these are terms or labels that humans know of. And when connected in this way, so it's human built. Although the actual knowledge is gathered and the processing is carried out by computing, which we call is a type of symbolic AI, we can call it symbolic AI. The advantages there is they're transparent, it's explainable, verifiable, and trustworthy. Right? Because so we can relate to that. It's in human language. Compared to what is on the right-hand side, this is what neural networks, deep learning, machine learning generated. The difference is that we don't engineer this. There's not human engineering. We have a data set and it's run through this neural network or a deep learning model, and it will change the weights. and create this, and it will give very accurate classifications, and it can be used for predictions, and it will build models with which you can classify and so on. It's data driven, it's very efficient, and there's not much human intervention required. But the main problem is black boxes, and very few applications would want to use such a system. That's the problem there. Then moving on, now, so there are obviously advantages and issues with the symbolic and the sub-symbolic. That is what we had in the past to, that is, say, from the 50s to about the 70s, 80s, and 90s, and then the machine learning, the neural networks, deep learning techniques. There are advanced. So what we call the neurosymbolic architectures, which are now being looked at as the basis of what we call the artificial general intelligence, is where we try to bring together the advantages of some symbolic and the sub-symbolic techniques. It's based on the idea that the human's brain process, there's the perception and cognition, two things or two ways that we bring information together. So perception is where processing raw data. Of course, the biological or the human perception is based on our the five senses that brings in our experiences and brings them together. That's processing, that we can call them in a very simplified manner as processing, ability to process the data. Then cognition is from the memory to the background knowledge, and together that supports aspects such as abstraction, analogy, reasoning, and planning, and so on. So it's these two together. So that's what the neurosymbolic architectures are trying to achieve. For the AI systems, that is integrate neural networks, the machine learning. When you say neural networks, it's the deep learning, machine learning, or models with the knowledge engineered models, such as symbolic architectures. So without going into too much detail here, because I don't think, again, this is on the more high-level discussion or a talk on what this is, rather than how it is built. That could be another talk somewhere else. So how we do is there's what we call the algorithmic level considerations, and then this integrated neurosymbolic architectures or neurosymbolic models will have the ability of abstraction, analogy, and long-term planning type of capabilities, as well as the really important capabilities of explainability, interpretability, and safety. And these are really required in many applications. For example, I work a lot with the healthcare domain. There's a lot of AI technology being used in healthcare, funded, the Australian government funded, and that really requires explainability, interpretability, and of course safety as well, as you can imagine, because who's going to accept an outcome from a black box model in a healthcare or any such application? Again, I don't want to go too much into details, but it's important to understand there are two types of AI machine learning. The pattern recognition is what we call mainly the machine learning. So you get a data set, you run it through a particular, what we call the neural network or AI, and then you get an output. It's almost as a one-off. So you're using the AI or machine learning algorithm as a tool to process this data to generate some output, which can be a classification, it could be a prediction, and so on. But model building is different. Model building is that knowledge is captured. It could almost like a knowledge graph, and that is maintained, and the model doesn't have, or it's not built specifically for just one purpose. It's about capturing that information as knowledge, and then the model can be used for multiple purposes. So that's, again, if we look at the artificial general intelligence that we are talking about, model building is much more towards AGI compared to pattern recognition, which is very narrow intelligence based. So what are the core ingredients? Again, lots of text. I'm sorry about that, but I'm just throwing some ideas at you to give a sense of what this is and what is required. So core ingredients of the machines the AGI or artificial general intelligence type is that one, it has to have what we call the environmental intuition. For example, even human infants have this have this ability, or they are born with this ability to understand that. So inanimate objects, for example, the big that are not alive, have, there's a continuity, solidity, and then even if you get a particular object that rigid bodies, soft bodies, liquids, that understanding is there. So that sensing is there. But think of an AI that we normally use. If many of you probably have experience with AI, the AI doesn't come with that knowledge. You have, every time you use it, the data, you would expect the data set to provide that. That is not how humans work. Humans do have that in some from birth, and some in a learned over time as they grow up. And this I'm going to, there's a term called latent learning, which I will introduce. It's not just an AI build for a particular data set to generate an outcome from that data set. Then the social intuition. Again, we are talking about AI that will coexist, that are not specifically built and only used for a particular activity, that can coexist in the community, doing things and experiencing and the particular environments, communicating. So in this case, social intuition has to be there. Again, I will very briefly mention how we are working on, or not only us, the AI researchers are working on providing social intuition to the AI, to move the current AI to the AGI. And compositionality is another factor, which is the new representations are built using the primitive or building blocks, or we call atomic elements, putting together, stacking these things in different ways, different structures to suit the environment. In fact, one of my main work is called structure adaptation, where we build the AI, or it's it automatically builds itself to suit a certain particular the problem or an environment, so that it will perform much better there. And causality, again, I don't want to go into detail there. It has to ability to cause. At the moment, it is not the case. At the moment, it's just based on the data. But just think of yourself, say two people or a group of people are communicating, and so there is somebody saying something, but we do not take that at face value. We know that person. It could be, it could be just a joke. It could be being sarcastic and so on. That is not really causality, but we need to go beyond just the data. So from correlation to causality is something similar as well. Learning to learn is again related, but it's not just the data, but what's underlying has to be understood or known to the AI, not just work or act or react to data as at face value. Again, I don't want to go into detail here, but there's another important factor that is really important in building or generating artificial general intelligence, is that the structural adaptation or growing nature. Now, there are two people, Alan Turing and more recently Jeffrey Hellman. They've said that it's easier to build and educate a child machine rather than create the adult. So that's an area. And then Hellman's work is also in that direction, in a general sense. So what it's saying that it's very difficult, or sometimes almost impossible, to build an adult AI, adult machine. So build a child AI, and then let it expose it to the environment, which is the digital environment, digital data, feed on it or experience it, and then grow to be an adult AI that can behave better. So there are, of course, all kinds of complications. It's not that easy. All right, so looking at the time also, I'd like to very briefly talk about some directions that CDAC stands for Center for Data Analytics and Cognition, which I have the privilege to lead at this point. In fact, I'm very proud to say that about 80% of the lab, especially of the PhDs, come from Sri Lanka. Some brilliant minds, and that is I'm so proud and so privileged to be able to work with these people. And we have, of course, academics and researchers from a number of different countries across the world. So there are, I've highlighted, this is not all, key 3 areas or what we call pillars on which we build our, we'll say our technologies towards an AGI. So latent learning is one, modality independence from multimodal fusion to modality independence is another area is called the social intelligence. Now, very quickly, what is latent learning? Now, it's a very important thing going towards AGI. Latent learning, so again, though, for those who you are familiar with AI or machine learning, reinforcement learning is the most widely used. But so in AI and machine learning, the main concept of training or making an AI learn is by giving it a reward. Reward is saying that if you do this, that's a positive, and if this is if you do that, this is negative. So that's reward-based learning. Now, latent learning is a concept that came about, that was introduced, in fact, a long time ago in the 1940s, by a guy called Tolman, where I said that no, humans do not just learn because of reward. In fact, learning happens out of curiosity. We learn, even if we are just put somewhere and then not given any reward or any purpose or objective, we still learn, and that's latent learning. So one of the key factors that we are highlighting for artificial general intelligence or AI, the future AI, is that capability of latent learning, and we are doing a lot of work in this area. So it builds what's called a cognitive map. And that's interesting that I'll just very quickly. So this is an experiment that was carried out by Tolman, they call Tolman in 1940s, and the paper is called Cognitive Maps in Rats and Men. Now it's a very interesting one. So I know that it's AI, not about rats, but I'll just explain what it is, and it's a very interesting point about why latent learning is important, and it does give us an understanding of many other factors or human factors as well. So what I highlighted in red is saying that it's an important thing as well. Reinforcement improves performance, but it impacts performance, but not the actual learning. So what you have here on the left side is a maze, and the rats were obviously introduced at the start, and there was some food, say cheese or something at the other side, and the rats had to find their way through. Now, on the graph on the right-hand side shows you there are 3 different groups of rats, red, green, and blue, we'll say. And there was one group, right from the beginning, the moment they were introduced, there was the reward at the end, cheese. So they very quickly, because they have a reward in mind, and they very quickly try to find so the blue one, always remember, the blue line shows how they performed. Very quickly they learned, their errors dropped, and because they are motivated to find the food. Then there's a green line, is no food was there. They were just introduced the maze, and they were just wandering around and so on. And they, of course, finally at some stage came out of the other end. But they obviously not very average errors were there. They took a long time. Then the red line is the most important part, where they the rats were introduced for 10, 11 days. They were just, going around without any reward. But after 11 days, they were given some food. Now, the moment that happened, you can see that the way that there was a drastic drop, and they even outperformed the rats who were given the reinforcement right. Now, you might think that what am I talking about? This is about to be AI, but I will tell you, hopefully, I think most of you must be getting the idea as well. So what we are seeing here is that this red group of rats, because they were running around, they were latent learning. They were building a cognitive maps in their brains of the layout of the maze. And they didn't have any particular reason to directly go into to the other side. But the moment that later, once the cognitive maps were built, the food was introduced, they knew different ways, more efficient ways of getting in there. That's what it shows. They did better than this because they had seen the whole sort of maze. And you can see that this could even be perhaps projected to, say, humans. If you learn something too much right from the beginning without getting an idea of the general scheme of things, you would be very efficient. Your performance will be even, but when things change, you may not fit into that. And this was even extended later by putting the blue and the red rats, a group of rats, by blocking some of the pathways that later the red group of rats could still find their way, while the blue group just got stuck. Anyway, I know that's a long story, but it's very important because latent learning, this is very, very important. Hopefully you get the idea of why we need latent learning for artificial intelligence of the future, of general intelligence. Okay, there's another, I wouldn't go to that detail into these other things which we are working on. So latent learning, we are building latent learning techniques, experimenting on. There are a number of PhDs working on these at the moment. And modality independence. So you must have heard of multiple modalities. That is, we can say images, audio, text, numeric data, and all that, bringing them all together so that you can build a combined, integrated, or fused understanding or perception of the environment. Now, multimodal fusion is one thing, but what really happened is that there's this concept that our perception, does it have a modality? We say that there is no modality. It's independent of modality. What is modality? Modality is created because we have 5 senses. We have our eyes, our ears, our skin for touch, and so on. Because of that, the way that we can even think of getting this environment or the perceive this environment, basically getting it into our, if we call it in a sense, the brain, then it is, so we have to use our 5 senses. So we have to break up this environment, which really doesn't have a modality, into the modalities, because that's the 5 senses we have. And then it goes in and it's combined together. And our perception doesn't have a modality as well. Our understanding, we wouldn't even know whether it came from images or the others or sounds and so on as well. Just imagine if there is an alien, say from Mars, and if that alien has other sensing mechanisms. Instead of eyes, it has something else and so on. We don't know what it is because we can't think of such thing. Then their modalities will be different from our modalities. So modalities are something that we created, and we are catering to. So because of that, we are talking about modality independence. We have found a way called hyperdimensional computing. This is my Swedish. We work with a university in Sweden, hyperdimensional computing techniques to achieve this modality independence. And then coming to the end, another very, very important idea is the concept of the theory of mind. It's a psychological concept. It's the philosophical and psychological concept of when as humans, the way that we can socialize we can communicate and socialize, be with each other, is that we have this ability, we continuously predict and model ourselves as well as the others. You are listening to me and you know you heard something about me, and whether it's accurate or not, you have built up a model or an understanding, or you have predicted something about me, and that's based on the human ability of what called the theory of mind. And in the recent past, we do a lot of work on that. It's called artificial social intelligence, ASI. So AGI has to have ASI if it is to coexist and interact with humans. And it's been called artificial theory of mind. It has been called machine theory of mind, and this is trying or an effort to create what we call artificial social intelligence. Now, that's a lot of things that I have thrown at you. And it's not just theoretical research we do. Unfortunately, I don't have time to go into this, but I will just finish this talk by giving you some idea of three projects in the healthcare sector. We work in many others, but healthcare is really important. And the one on the left-hand side, what we call the artificial intelligence co-facilitator, is with healthcare researchers, cancer researchers in Canada, and the Ontario Institute of Cancer. It was funded by a Canadian cancer research fund, where some of our work was built into an online cancer care program, where there's cancer patients register in this online, and then they communicate with psychologists and other helpers and facilitators, and that conversations are captured, and they run through the AI that we have built, and that profiles this person, understand these people, their feelings, their emotions, their emotion fluctuation patterns, and so on, and that helps the caregivers to provide a better care. And this is an online system. It's called Cancer Chat Canada. That is, so it's currently implemented. And the other two are very large, what you call NHMRC grants. NHMRC stands for National Health and Medical Research Council of Australia. So it's a large government grants. Each of them is about a couple of $1 million worth over 5 years, both about post-stroke rehabilitation. Communication Connect is aphasia patients, people with after stroke. Some people have aphasia, that the communication disabilities, and we are working with a large group of clinicians. So I'm the only non-health person in this. So I'm trying to helping this, that to understand that technology and AI works hand in hand and as part of a team of medical doctors, therapists, and so on, to bring in technology, build artificial intelligence that can profile, that can do audio analysis, and build apps with which we can provide a better service, better care, so that these people can live at home and provide therapy. We are building online Zoom-based therapy techniques using artificial intelligence as well. The Staying Connected, the last one on the right-hand side, is again a 4-year project currently on post-stroke rehabilitation and providing care. So that technology going to artificial general intelligence and this. So do we need it or not? I think my purpose being I'm biased, but artificial general intelligence is something that we require, because we live in an environment where the standard AI will become obsolete. It's already becoming obsolete. It's not, so we do need AGI. But of course, there are the dangers, and you must have heard of all the potential dangers. But then it's up to us humans to make sure that we use it responsibly, and also put in constraints and restrictions where possible. Thank you so much, and hopefully I didn't go over time. And if happy to take any questions.
If there are any questions for Professor Damminda, please do raise your hand and the mic will be brought to you. Yes, we have one question.
Damminda, so I like the fact that you use ASI for artificial social intelligence, but what about, what about the other ASI? What do you think about that? Artificial super intelligence.
That's that's a controversial. But first of all, there's what I would say is that will there ever be? Unfortunately, I say unfortunately on purpose that things are going in that direction. That ASI, it's perhaps a next stage of AGI leading to ASI. Yes, it can be very dangerous, but then will it stop humans? It's part of being human, I think. Now, I would not, even now, sometimes I do think back and say, do I really want to continue this work, even in some of the things that we do? But as humans, I think I don't know whether for it's good or bad, or it's just a human nature that we continue to build this, and it will come. It will come. What we need to do is find ways to protect ourselves just from as technology. But look, I don't have a real problem, but there definitely is a huge danger with that ASI.
Thank you. Are there any other questions? Any other questions? All right. I think there are no more questions at this time. Professor Damminda, thank you so much for being with us. It was a pleasure having you. Thank you so much for that speech.
Yeah, thank you. Thank you for the invitation. I really appreciate it. Thanks.